Okay, it's my very great pleasure to welcome Professor Jocelyn Bell Burnell to give the Hofstadter lecture, or the second Hofstadter lecture. We have the Hofstadter lecture, and it's always two lectures, and this is the second one. And you have this program, or you should have this program with quite a lot of details, both about Robert Hofstadter and also Jocelyn Bell Burnell. And so let me just summarize a little bit by way of introduction. Prof. Hofstadter was here at Stanford from 1950. He was a professor from 1950 to 1985 and continued teaching after that. He, amongst many accomplishments, he won the Nobel Prize in 1961 for his work on electron scattering and understanding the structure of atomic nuclei. He also, almost as a second career, got involved in gamma ray astronomy and was a pioneer and designer and inspiration of EGRET, which is one of the major instruments on the Compton Gamma Ray Observatory. I think he passed away just before launch, but that was extremely successful, and the mantle was passed to Peter Michelson, who is here in the audience, and he led that for 9 years until it was deorbited into the ocean, and then was followed by another gamma ray telescope called Fermi Gamma Ray Observatory, and there were many connections. Obviously the biggest one is the instrumental connection, where the ideas and the methodology that Hofstadter pioneered continued in the Fermi Gamma Ray Spectroscope, but also the use of the word Fermi. I think he was the person who coined the unit of the Fermi, which is commonly in use in nuclear physics. And Fermi is still going great, and Hofstadter's spirit lived on in this mission. Even this morning, I got a wonderful new paper drafted from Fermi. I'm not allowed to tell you what it's about, but it's a new set. It's been going for 15 years, and it's still making discoveries, as you'll see from the paper on mining your whale box this morning, and you will hear about before too long. So it's been a great success, and he pioneered a new field. Also, we'd like to introduce Doug and Laura Hofstadter, who are here joining us here, and thank you very much for joining us and for all you have done for this lecture series. And this morning, Doug sent me an email about it was a copy of a proposal that his father had written in 1966 to use X-ray astronomy, not gamma ray astronomy, but X-ray astronomy, to look in particular at the Crab Nebula and see if there was a neutron star there. Now, there is, but this was 1966, and the papers that had proposed that this might happen happened a year later. So this was an extraordinary prescient proposal, and as a consequence, it was not unsuccessful, but it shows you a little bit about Hofstadter. So I now turn to Jocelyn Bell Burnell, whose her current position is a visiting professor of astronomy at Oxford. She has had, she's going to tell us about pulsars, and she, as a graduate student at the University of Cambridge in 1967, she made this wonderful discovery of pulsars using radio telescopes, and their almost immediate interpretation as neutron stars. And she has gone on from that to explore not just radio astronomy, but the whole electromagnetic spectrum. And her career has taken us, as I say, from the smallest frequencies to the very highest frequencies in astronomy. And she's also had a lot of leadership positions, including being president of the Royal Astronomical Society and the Institute of Physics. She's in the Royal Society, where she won the Copley Medal, and in the National Academy of Sciences, and so on, many distinctions, including quite recently, the Breakthrough Prize here in Northern California, where she very generously donated the monetary gift that comes with this for helping women, underrepresented minorities and refugees get a start in physics. So I think there's an awful lot to commend, and I'm really thrilled personally that Jocelyn is here. I'll give a sort of a personal note here. That when I started as an undergraduate in 1967 in Cambridge University, and the very first talk I'd ever heard in public on astronomy was in the Astronomy Society, and guess what? It was about the discovery of pulsars. This was, very soon after it happened, and it has to be one of the best I ever heard. Pulsars and neutron stars are the gift that keeps on giving. And this has been a wonderful discovery with as large a font D as you can possibly put in it, and they're still discovering, and there's almost no area of physics that isn't represented one way or another in a neutron star. So please, Jocelyn, allow me firstly to welcome you. Thank you for coming to talk to us, but also for the wonderful gift that you have given us. Thank you very much indeed.
Thank you very much. Thank you very much for that generous introduction, and thank you all for being here this evening. So as Roger has already indicated, this is a story from quite a while back. I think the main thing I need to point out about conditions way back then was women in science were a good deal fewer. Women doing anything in a leadership role was pretty unusual. And I will talk a little bit about the attitude of the press to me and to my male supervisor later on. Older people in the audience will probably recognize exactly what I'm talking about. I dare say the younger ones will be horrified, and quite rightly so. So I'm going to say a little bit about my background. I'll try not to dwell too long on that. Then this is a story from radio astronomy. And I'm going to say also a little bit about some incidents that other scientists have told me. Because one of the privileges of discovering pulsars is every so often somebody comes up to me and says, I nearly discovered pulsars, and tells the story. And these stories also reveal how science works and the kind of things that can happen in science. And if time doesn't run out, which it might, I'll reflect a little bit on the factors that led to the discovery. So I'm not American, as you can perhaps already deduce. I started life in the north of Ireland, which is a fairly small community, and was sent away to boarding school at age 13, so that I had some of my education in a rather broader community. Marginally broader, they sent me to a Quaker girls' boarding school. I started my brilliant academic career by failing a crucial exam that we all had to take at age 11. It was believed at that stage that you could tell by age 11 whether a child was going to be academic and needed that kind of education, or whether something more practical would be appropriate. And I failed that exam. I have to say it wasn't entirely my fault. There was a higher pass mark for girls than for boys, because everybody knew, beware of everybody knew that girls were only going to get married and be stay-at-home housewives and mothers, and they didn't need this superior education. It was the boys who were going to be the wage earners that needed it. So I was at risk of not having a very good education for failing this exam, but fortunately the school in England didn't care about whether I'd passed that exam or not. A girls' boarding school had some trouble getting science teachers and maths teachers. I can remember our chemistry teacher. We had a display of the periodic table up on the board. And we'd say to him, why are things laid out this way? What is it? And he said, God made it so. Might be true, but there are other explanations that maybe would be more educational. Our physics teacher was fantastic, but elderly, come out of retirement a second time to teach us. And the maths education was pretty good. But girls' schools did suffer from getting good science teachers. I had decided as a teenager that I wanted to be an astronomer. Temporary glitch when somebody said to me, you know, astronomers work at night. That hadn't occurred to me. Astronomers work at night, and so you have to be good at staying up. And I knew I liked my bed. But then I discovered radio astronomy. Optical astronomy you do at night because the sun washes everything out in the daytime. But radio astronomy you do day and night. And most astronomies that we do these days, you do day and night. So I discovered radio astronomy a few years later and said, right, I'll be a radio astronomer. And that's what I did do. I decided it was wise to do a general physics degree. Went to the University of Glasgow in Scotland. That was quite hard work, not academically, but for other reasons. It was the tradition in Glasgow at that time that when a woman entered the lecture halls, all the guys whistled, catcalled, stamped, pummeled their desks, made as much noise as they possibly could. And if you blushed, they made more noise. I learnt to control my blushing. It was essential. I think I've lost the technique, but that was one of the things I had to acquire as an undergraduate in physics in Glasgow. I did the 4-year degree. I ended up being the only female in an honours class of 50 students. I was living in a women's residence, and the other women said, oh, you'll be changing subject then, Jocelyn. Well, I wasn't. But it was quite tough, I must admit. And the lecturers did nothing to stop the barrage of noise that my male students would make when I entered the lecture theatre, when I answered a question, anything like that. It was considered the norm. And I hoped to go to Jodrell to do a PhD in radio astronomy, but they never replied to my letter. I'd worked there the previous summer, and some grad students had told me that they wouldn't take women. They had once had a woman, and she and one of the male grad students had put the dormitory accommodation to a use for which it wasn't intended. The head of the observatory, Sir Bernard Lovell, got to hear of this and said, no more women. Interesting which sex bears the brunt of these mutual encounters. So I gave up on Jodrell Bank. I didn't think I'd get into Cambridge. I reckoned I was going to Australia. But the academic year in the Southern Hemisphere begins January, February. I had a few months in hand, and I put in an application to Cambridge just in case before I headed to Australia, and very much to my surprise, got a place. On arrival in Cambridge, my comfort was discomforted. New graduate students in radio astronomy were each presented with their set of tools. These are mine. These are not microelectronics tools. These are full-sized wire-working tools, and I was going to be using them a lot. I still have them. They were actually the first tools I ever used. And this is about 2 years in. I've been spending the first 2 years helping build a radio telescope. Here we are checking out some low-loss cables to ensure that the connectors I've put on either end are making good connection. You can see a little red and white hut behind me. You can maybe see another one in the distance centre back. We had this low-loss cable that you could not coil up and take indoors. So through the Cambridge winter, I sat in those two little huts putting plugs and sockets on the ends of the cable. And we're now checking the connections are good. Physicists may recognise a slotted waveguide in the foreground. Doing anything out in the field, several hundred yards away from the nearest power supply, is actually quite difficult. It's cold, it's wet, and maybe your power isn't coming through properly. And trying to use a soldering iron is really difficult because the wind cools things too quickly. But you do it somehow. So that radio telescope, you can see some of the, or the radio telescope it's intended for, you can see some of the statistics below. 2,048 dipoles, over 1,000 wooden posts, 120 miles of wire and cable, and an area of 57 tennis courts. It's big, but it's big in part because the frequency is low, so everything is large. And it took 6 of us, mostly grad students, 2 years to build. This is the finished article. It's working at quite a low radio frequency, so really you can barely see the antennae. You can perhaps see some looped copper wire that's showing nice greeny colour. That's the feeds down from the antennae. And the wooden posts, which are the most obvious thing, only do the job of keeping it all up out of the wet grass. So what was all this about? Well, at that time, radio astronomy had recently started, and it had found some very strong radio-emitting objects up in the sky. And gradually they got better positions for them, and the optical astronomers would say, well, there's something a bit like a star there. It's not a star like we've ever seen before, but it's sort of star-like. And these things became known as quasi-stellar radio sources, or quasar for short. And there must have been about 20 known when I started. They were quite a puzzle. The optical astronomers trying to make sense of the optical spectra were really puzzled. And there were 2 astronomers in Caltech, each with a spectra of a different quasar, trying to make sense of it. And one astronomer is writing a paper trying to explain why this object is full of ytterbium, because ytterbium was the only thing that even faintly matched the spectrum. That was Jesse Greenstein. Along this way, in another office, another astronomer looking at the spectrum of, optical spectrum of another quasar. Looks a bit like hydrogen, but it's in the wrong part of the spectrum. It's very, very red. Could it be hydrogen? The spacing of the lines is right for hydrogen. So Martin Schmidt begins to wonder if he's seeing a hydrogen spectrum with a large redshift, which would mean the thing giving that light was receding at considerable speed from us, which probably meant it was at a huge distance. This was several big steps, too many all at once. So he goes along the corridor to his colleague who's trying to write this paper about ytterbium and says, Jesse, could it be hydrogen with a large redshift? Oh. Jesse's redshift was comparable to the one that Martin had found, not the same. And it turns out that they were right. These are very, very distant objects. We still see them as very strong, very bright objects. So intrinsically they must be extremely bright, and they were a considerable mystery. And at the time I joined the story, there are only about 20 of these objects known, and it's a very small sample. And the purpose of this radio telescope was to find a lot more. The quasars are good, strong radio sources, and if you observe a distant object from the Earth, you're looking out through the space of the solar system, past the sun and past the planets and out way beyond them. And that space between the planets is not empty, because the sun has a wind that blows out and carries what's called ionized material, charged material, out into the space between the planets and probably further. And this flow of material out is not smooth. It's a bit lumpy. There are some patches where there's a higher electron density and some patches where there's a lower electron density. So it's like having clouds in the sky, because these patches will affect radio waves differently. And on the right, I'm trying to illustrate that. Way up the top, way up beyond the lights, is a quasar, one of these objects. And the signal, radio signal from the quasar is coming to a radio telescope on Earth. And to get to Earth, it goes through the space between the sun and the planets. And that space is full of this, what we call solar wind. For the physicists in the audience, there are clouds with increased electron density. And that pattern of clouds and gaps acts a bit like a diffraction grating. And so the radio waves coming through get spread out into several discrete beams. But because this is part of the solar wind, that whole thing is blowing sideways. And so sometimes you see the quasar through a cloud of extra electrons, sometimes you see it through a gap between the clouds, sometimes you see it through another cloud. And down in the bottom, I've illustrated the fluctuations in intensity that you would typically get. Quasars do this particularly because they're very compact. Most other radio sources are quite broad, and you're viewing the broad radio sources through several clouds and several gaps, and you don't get the same jumping in brightness, the same intensity fluctuations. So we have a neat technique for picking out quasars. Survey the sky regularly, just watch the sky go past and look for radio sources that go and that'll be a quasar. But you have to have quite a short time constant, another technical piece for the physicists, which means your signal to noise is worse, which you have to compensate for by having a very, very big radio telescope to collect lots of signal. At that time, the University of Cambridge, the whole university, had one computer. It was built with vacuum tubes and it occupied a whole room, and it had memory less than a good laptop. And very, very few people could get time on it, and we couldn't. So our data came out on paper chart, which the grad student, me, analysed by hand. There was really rather a lot of that chart paper. I was getting 100 foot of chart paper every day. And running the survey for 6 months, I had 3.3 miles of paper chart, which I had dutifully analysed every quarter inch of it. Now, whoops. Yep. Okay. So we've got this repeated mapping of the sky to try and pick out these twinkling quasars. And measure their angular diameters, but that's another story. You'll have seen that I was looking for fluctuating signals. I need to observe with a rapid response piece of equipment to pick up the signals. Technical phrase, a short time constant. And I did 6 months observing. I got over 3 miles of that paper chart, and I found, I've forgotten the number now, something like No, I can't remember. But I increased the number of known quasars by a factor of 10. So as a PhD project, it worked beautifully. But it wasn't all plain sailing. Remember, I'm in this place that's full of very, very bright young men. And I'm a woman from the provinces. And I shouldn't be there. They've made a mistake. So I'm working very, very hard. And being very, very conscientious over that chart recordings, checking them really, really thoroughly. And just occasionally, there was a signal I could not understand. I quickly got to recognize the scintillating, twinkling quasars. That was fine. Big radio telescope like that will pick up quite a lot of interference. In those days, cars were badly suppressed, and a car driving close by the telescope would send the pen recorder wild with radio interference. Pirate radio stations were a nuisance. Somebody allocated the local police for their radio cars our frequency. They shouldn't have. These frequencies are protected, but they'd made a mistake. And cars were very badly suppressed in those days, so a car going down the local road gave a signal. So all sorts of things gave interference. And up on the right, I have a high-pass filtered version of the data. In other words, I've taken out slow, drooly fluctuations. I'm looking for faster fluctuations. And on that particular chart, you can see two pieces of fluctuation. The right-hand one is some low-level interference. The interference could be bad, and the pen would go from end stop to end stop, but that's relatively low level. And on the left-hand side, there's a signal that I couldn't make sense of, which actually turned out to be the pulsar. And I think if you've done much looking at signals and charts, you might agree that those two don't look quite the same. They look different. For instance, the right-hand one, the spikes go up and down. The left-hand one, the spikes go mainly up. The right-hand one, you can see chart between the spikes. The left-hand one, there are certainly places where you can't see chart between the spikes. When you say the spikes go up and down, or up only, you're talking about the amplitudes. When you say you can see space between the spikes, you're talking about the frequencies present. I'm hoping there are some physics and math students in the audience who have learnt or will learn about Fourier analysis. You are doing Fourier analysis when you say, I can see gaps there, but not there. Spikes there go up and down, spikes here go up. You're commenting on the amplitudes and the frequencies present, and that's what Fourier analysis is. Or put differently, they look different. Apologies to the physicists, but they look different. And that signal on the left wasn't always there. You can see the statistics in the text. But when it was there, it was coming from the same bit of sky. Now, the sky takes 23 hours, 56 minutes to go round and come back again. It gets 4 minutes earlier every day. That signal on the left was getting 4 minutes earlier every day. Interference, like on the right, could happen at any time of day. But just suppose the left-hand one is interference. Just suppose Joe Doak's driving down the road in a badly suppressed car. Well, Joe is getting off work 4 minutes earlier every day, 28 minutes a week, and this has been going on for quite a few weeks. The only people who keep to that schedule are other astronomers. Or the sky. But it wasn't always there. It was quite a puzzle. I showed it to my supervisor, who said, "You stupid fool. Usually conversations with my supervisor did have that kind of tenor. You stupid fool. And I thought, oh my God, what have I done now? He says, it's all jammed up into about 1/4 of an inch. We can't see what's going on. We need an enlargement. And with this chart technology, enlargement is easy. You run the paper faster under the pen and it all gets spread out. So we run the paper faster under the pen. And it gets through a roll of paper in 20 minutes. And whose job is it to keep rolls of paper in the chart recorder? The grad student. So if we run the thing faster, the grad student's going to live at the observatory, putting a fresh roll of paper in every 20 minutes. We need a better idea. Next better idea. The grad student goes out to the observatory shortly before that signal on the left is due to appear and switches to a high-speed recording, lets it run for 5 or 10 minutes, switches back to normal and gets on with all the work she should be doing. And I do that for a month, and I make high-speed recordings of receiver noise. The thing, whatever it is, has disappeared. And that's the grad student's fault as well. Finally, I catch it. The labeling comes later. I'll explain that shortly. The bottom trace is 1 second time pips. The middle trace is the signal that I picked up. And you can see that there is a string of pulses. They're separated by 1 1/3 seconds, approximately. Some of them are quite strong, some of them are weak or even missing. But even where they're missing, it doesn't miss a beat. It recovers and the next pulse comes back on beat. And it's a period of about 1 1/3 seconds. So this is the very first trace detected. LGM1. LGM stands for Little Green Men, which was my nickname for these things. I wasn't seriously believing that it was extraterrestrials, but you can't keep talking about, that funny source at Right Ascension 1919 and Declination 23. It's too much of a mouthful. But you can tell that that caption was added later because of the 1. You don't label the first thing number 1. It's only when you have more than 1 that you go back and label it number 1. So that caption is added afterwards in my supervisor's writing. For physicists in the audience, the pulses rise and fall quite steeply, which implies it's a small object. But as I kept recording this thing, it became clear that the period was very, very accurately maintained. It was not getting tired, which means it has big resources. So it's small and it's big. Aha. More about that anon. Well, radio telescopes, especially big ones, pick up a lot of radio interference. But as I've already mentioned, if this is Joe Doak driving down the road, he's getting 4 minutes earlier every day. Radio interference is terrestrial and doesn't normally keep pace with the stars. So that was a little bit hard to explain. But maybe Jocelyn has wired something up wrong, and that's what's producing this funny effect. So rather discreetly, we talked to another grad student and his supervisor. That grad student also is using a radio telescope that works at the same frequency. And we asked whether, his name was Robin, whether Robin and his telescope could possibly pick up this signal, or was it really something created by my equipment? And I remember that test rather well because it really was an acid test. The way the telescopes were aligned, mine saw the object first, and it was pulsing away nicely. And then four of us, me, the other grad student and the two supervisors, went and stood by the pen recorder for Robin's telescope. And nothing happened. And the two supervisors started walking down this long, long laboratory, and I was tagging along behind them. Robin stayed at his pen recorder. Now, what could it be that shows in yours? But do you think it could be? No, it can't be that. But I wonder if, oh, yeah, no, but then, and the discussion went on. And suddenly there was a shriek from Robin, "Here it is!" And we went charging back up. And yes, Robin had miscalculated by about 10 minutes when his radio telescope would see this bit of sky. If he'd miscalculated by 30 minutes, we might all have gone home and the story would be different. So it's seen by a separate radio telescope, its own wiring, its own electronics, its own receiver, even its own pen recorder. It's something beyond the radio telescopes. It's something up in space, and it's not my fault. The other thing we began to recognize is that the pulse period's quite fast. The pulses have quite steep sides. The pulse period is accurately maintained. The steep-sided pulses implies it's a small object. The period being accurately maintained suggests it's got large energy reserves, so it's big. So it's big and it's small. Doesn't really make sense. That was something we had to work at. A colleague took two of my receivers, because by that time I was observing with 4 different beams simultaneously, so I had 4 receivers, 4 beams. He took 2 of my receivers, tuned one up in frequency a little bit, tuned one down in frequency a little bit, and after a lot of false attempts, managed to pick the pulsar up in both receivers. And the signal came first in the higher frequency one and then in the lower frequency one. So the signal is like, if you listen to it, can't whistle properly, a descending note. Now, this is a sign to scientists. This kind of phenomenon was first spotted by people who studied the various radio clicks and things that you pick up around the Earth, terrestrial geophysics. If there is a lightning stroke on the far side of the world, it generates a radio signal which travels round a big loop of magnetic field and comes down here and is picked up by your receiver. But there are electrons along this route, and the electrons slow up the low frequencies more than they slow the high frequencies. So the signal that reaches you is what we call a whistler. It's a descending note. I'll have one more go at whistling it. And the geophysicists knew about this, and they used that technique to estimate how many electrons the signal had come past, and to get some idea where the signal was coming from. In the case of geophysics and in the case of Britain, it's lightning strokes in New Zealand produce a radio wave which propagates right down, comes back in Britain as one of these whistling radio waves, called a whistler. Now, you can do the same technique with any pulsing radio signal. You can take 2 receivers and see what's the time delay between high frequency and low frequency. And my colleague did this and got a time delay and made an estimate of how many electrons, how many free electrons there were in space, and thereby got an estimate of the distance of the source. And it came out to be about 200 light years. Light travels 186,000 miles per second. In 200 years, it goes a lot of miles. So this is a distant object. It's out in space. It's quite far out in space, well beyond the galaxy. So what's causing it? What's going on here? Well, we'd already begun to nickname these things little green men, because that's the picture we have of extraterrestrials, you know. Little men, bright green, extraterrestrials. So they're little green men. Maybe, or maybe not. I sincerely hope they weren't. And my supervisor recognized that if it was little green men, they probably live on a planet. And their planet goes round their sun. So some of the time their planet is coming towards you, the radio astronomers, and some of the time the planet is moving away from you, the observers. So if this thing is a planet or something like that, and it's producing pulses, as it's coming towards you, the pulses pile up on each other, get closer together, and as it's moving away from you, the pulses get further apart. This is what's called Doppler effect. So, Jocelyn, keep making observations of this thing, keep measuring the period between the pulses. We want to see if there's a Doppler effect. And there wasn't. So this thing wasn't, well, if it was orbiting, it was a very, very tight orbit. It wasn't doing any plausible kind of orbit. It was kind of stationary, whatever it was. And the next step was that I found a second one. The day before, a few hours before I left Cambridge with my boyfriend to go to my parents to announce our engagement to be married, I'm, of course, in the laboratory busy analysing and looking at data from a totally different... Oh, that looks interesting. I wonder, is that another one of these? Oh, I should check previous records from this bit of sky. I have a shelf full of shoe boxes with previous records filed by which strip of sky it is. I get out that shoe box. I spread the things out on the floor. The grad students were in an attic with a great big corridor along the middle. It was fine for spreading out miles of paper chart. Line them up. So it wasn't there. Oh, it might have been there. No, didn't see it that time. Oh, I didn't notice that, but it was there then. No. Maybe. No. Yes. Yes. And this one. It looks as if there might be another one from a totally different bit of sky. That bit of sky is visible to my telescope at about 2:30 a.m. and I have to be there. So I go out to the observatory at 2:30 a.m. I'm driving a little motorbike. Not fun on icy roads in December, on your own at the dead of night. But got there, got the recording set up, and in came pulse, 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 pulse. So I put the record on my supervisor's desk and said, "Tony, another one!" And went off with my boyfriend to my parents to announce our engagement. Came back. Tony had very kindly kept the survey running over the Christmas break while I was away, which means he put paper in the pen recorders, ink in the wells, and placed the recordings, the charts that have been recorded, on my desk to be analysed. And there's a pile of charts like this. So he's in a meeting. I can't see him just yet. I sat down to do some analysis, working my way through this. It's not a terribly exciting job. Which one's that? It's not either. It's another one. Get out the other chart recordings for that. Okay, out comes the shoebox, out come the chart recordings. Whoa, yes, wasn't there so often, but there might be something there. Right, I've got about another 3 foot of chart paper to finish. Shove all that stuff out of the way. What? 2 of them on the same piece of chart recording? 3 foot apart? At that point, my supervisor appears and stands at the end of the desk. "Hey, Tony, look. Oh, Happy New Year, Tony. Thank you for keeping the survey going. Look at this, look at this. 2 of them." Huh. How many more have you missed? go back through all your old records and check. So it took me about 2 weeks to go back through all the old records, and I didn't find any more candidates, but we confirmed those 2 candidates. Third one was particularly interesting because it was pulsing at 1/4 of a second. The other 3 were all a period of about 1 point something. So one of them's going much, much faster, which is interesting. We write up the first one, get it ready to send off. The other 3 will come in a subsequent paper, particularly when we've done a bit more measurement on them. And the paper is going to Nature, which is a fairly prestigious journal in Britain. And the evening before the paper is due to appear, Tony gives a colloquium in Cambridge and gives it a very titillating title. And every astronomer in Cambridge comes, including the theoreticians who didn't often take an interest in radio astronomy. At this stage, we are aware that there could be 2 possible explanations for this kind of behavior. You could have something that's oscillating and launching shocks into its atmosphere, and the shocks somehow generate radio waves. Or it could be spinning like a lighthouse and sweeping a beam around that shines on your radio telescope once every revolution. An oscillating object would be what astronomers call a white dwarf. The rotating thing would probably have to be a neutron star, which at that stage had never been seen, but some mad theoreticians had this idea. And Tony favours the oscillating white dwarf model. You can ultimately tell the difference because as an oscillating object tires, it gets faster but lower amplitude and stops. Whereas a spinning thing gets slower as it grinds to a halt. But we didn't at that point have the data to be able to say which it was. So Tony gives this colloquium a very titillating title, and every astronomer in Cambridge comes. Fred Hoyle sits in the front row. Some of you may have heard of Fred Hoyle. A fairly blunt northern Englishman, wrote some wonderful science fiction books, wrote 1 or 2 quite good astronomy books. In character, didn't get on terribly well with some people and was inclined to say exactly what he thought, whether it was tactful or not. So Fred's sitting in the front row. Tony does his explanation, ending up with he thinks it's an oscillating white dwarf. Questions at the end, Fred is the first to speak. I don't think it's a white dwarf, in his Yorkshire accent. I think it's a neutron star. And he was right. In 40 minutes, that man has heard the evidence from scratch, with no previous warning about what this was, and hit the right explanation. But it took quite a while until we were able to, or somebody was able to confirm that, because you needed to be able to establish whether the period was getting slower or whether the period was getting faster. Faster if it's oscillating, slower if it's spinning. And we now know that they slow down. So we wrote up the other 3 later on, and there was a lot of press interest in that first paper. And the press would arrive and they'd meet with Tony, and Tony would give them, you know, the spiel and the astrophysical significance and so on. And then one of them said, was there anybody else involved? And oh yes, Tony said, he's got this grad student, she's not here. Get her here. So I had a phone call, you know, take a taxi out to the observatory. Such and such a newspaper wants to speak to you. And that was a very weird and a very uncomfortable experience. This is 1968. There weren't many women scientists. There weren't many women in professional roles. Women were perceived by the male press as sex objects. And so the interviews with Tony and I by journalists typically took the pattern. They asked Tony about the astrophysical significance of this, and they asked me for my bust, waist and hip measurements, and how many boyfriends do I have, and would I describe my hair as brunette or blonde. Only 2 colours were allowed. And the photographers were even worse. They said, please can I undo some buttons? That kind of thing. It was really, really horrible as a young woman at that stage. And nobody seemed to think there was anything strange about it or unkind about it. I was by that stage engaged, which protected me a little bit. But even so, pretty horrible. But there was a lot of interest, I have to say. One of the journalists actually created the name Pulsar. The Daily Telegraph, it's a very conservative British newspaper, which I wouldn't normally read, but it did have quite a good science correspondent at that point, Anthony Michaelis. And he said to us, what are you going to call these objects? And we had already thought a bit about this. They could have been pulsating radio stars or pulsed radio stars. But pulsed implies there's an agency creating the pulses, little green men. So we said very firmly, pulsating radio star. But that wasn't good enough for Auntie Michaelis. Too long. You want a shorter name. What about pulsar? We already had quasar, so this was kind of modelled on that. And pulsars they became. And it was he who named them. One of the privileges of being involved in this discovery is that for quite a long time afterwards, people would come up to me at a conference and say, you know, I nearly discovered pulsars, and tell the story. And if you're happy for me to go on just a little bit longer, I'll tell you some of these stories. So the first one is from way, way back, late summer 1957. We are at McDonald Observatory in Texas, I think it is. McDonald has specified that this telescope has to be open to the public one night a month, and it's the night that the telescope is open to the public. The telescope is set on the rather curious star in the centre of a nebula that we know as the Crab Nebula. We now know it's an exploded star, and we know that there's a pulsar in the middle of that nebula. A very fast pulsar. Goes at about 30 pulses per second. And people step up to the telescope and say, oh gee, or hey, wah, whatever they said in Texas in 1957. And a young woman steps up to the telescope and says, that star's pulsing. And the night assistant starts to explain about the way stars twinkle and scintillate. He says, stops him. No, I know about that. That star's pulsing. My job is as an airplane pilot. 1957, a young woman. I fly newly constructed aeroplanes from the manufacturer to the customer. I fly at night. There's not a lot to do in the cockpit at night. I look at the stars. I know that stars twinkle. This is not twinkling, this is flashing. Nobody followed up. There is, in the middle of the Crab Nebula, a funny star which is a pulsar, which flashes 30 times per second. It's close to the limit of human perception, but some people, particularly young women, can see that frequency. And we know that because in Canada, the main power supply used to be at 30 hertz. And a number of young women were driven mad when all the lights and everything are doing this, if they can see it. So some people, particularly young women, can see 30 hertz. But nobody followed up. Rather more recently, the Australian radio astronomers have an online catalogue of pulsars. And somebody outside the pulsar community has just found this and sends them an email message saying he was a United States Air Force technician 1967-68, based in Alaska, excuse me, at the early warning system, looking for Russian missiles coming into the USA. Very powerful radars, very good receiving equipment. And when things were quiet, his boss would allow him to play around with the kit. Now, I don't know who this was, but bless them. He had taken an astronomy course at college. He knew about right ascension and declination, how we give the coordinates of stars. And all these years later, he can still remember right ascension and declination. So he's playing with this equipment, and he finds a number of things in the sky that flash. 14 possible sources. And he notes the right ascension and declination, the coordinates of these, as best he can, on a little piece of paper, which he should have left in Alaska when he left the military. But somehow that little piece of paper went with him. And he has just discovered the online pulsar catalogue that the Australians keep, and several of his pulsing sources would appear to be in it, including one which is called the Crab Nebula. Australian radio astronomers worked with him Australian radio astronomers worked with him quite a bit. They do believe he was genuine. They do believe that with that ballistic equipment in Alaska, he had picked up radio signals from pulsars. And as I said, one of them is the pulsar in the Crab Nebula. He came to some of our conferences for a while, enormously enthusiastic about all this and getting a sort of explanation and closure on what he did when he worked for the military. Sorry, my laptop is not behaving very well. Right. Third example involves a Canadian woman called Sue Simpkin. I mentioned that she's Canadian. She was brought up in Canada. Remember I said earlier, Canada's main power supply used to be at 30 hertz. She was one of the young women who could see all the lights and things flashing. She knows she can see 30 hertz. At this point in her career, she's working in ultraviolet astronomy, and an eminent Dutch astronomer, Lo Vulture, asks her if she'd take an ultraviolet spectrum of that funny star in the middle of the Crab Nebula, which we now know flashes 30 times a second. She said the spectrum was dull, but as she observed it, she could see waves going out. When she told Lo Vulture, he said, "No, can't be." But when the Crab pulsar, the pulsar that she was observing inadvertently, was discovered, he was man enough to say, "You probably saw it." The final example, I'm not naming the people. They are no longer on this earth, but they were always really rather embarrassed that they hadn't quite pulled this one off. They're radio astronomers making a map of the whole sky in radio waves. It's a huge project. They've got some time on that big radio telescope, some time on that radio telescope, some time on that radio telescope, and they've almost completed their survey. There's just a few gaps left to fill in, and they're busy doing that. This is still in the era of pen recorders. One of their pen recorders is a bit sticky, is a bit misbehaving. And one day at 3 o'clock in the morning, that pen recorder starts going wheep, 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 wheep. And the astronomer observing at 3 o'clock, 4 o'clock in the morning says, "Oh, damn it, that pen recorder." And does what we always did to pen recorders, thumped it. It resettles things, improves the connections. So he thumped it, and it stopped going wheep, 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 went back to normal. We now know that he was observing a pulsar. It wasn't a fault of the pen recorder. The pen was picking up a series of pulses. I'm sure there are physics students here who've had people yell at them because they're not writing up their logbook. This is why you have logbooks. He didn't write it up. There's nothing in the logbook. if he had, he could have claimed prior discovery of a pulsar, because that's what was going on. Yep, I think I've said all of that. So to close, I think I will close, it's probably time I closed. I want to pay tribute to a particular Italian astronomer called Franco Pacini. The object we call the Crab Nebula was a great puzzle to many of us. It's the remains of a star that exploded in 1054 AD. We know that. 1054 AD is quite a long time ago. The nebula, the stuff left over from the explosion, ought to have faded. It hasn't faded. It is not obviously fading. Something is keeping it energized. And Franco Pacini hit on the right explanation, although it took a discovery of pulsars to really make people believe he was right. He said, supposing there's a very compact star called a neutron star. We call it a pulsar today. It's spinning fast, it's got a strong magnetic field. Magnetic field is offset, so it cones around, heats, energizes the nebula, keeps it shining, as long as the frequency of this is high enough that the energy won't escape from the nebula. Otherwise, it'll simply escape and the nebula won't shine very well. Yep, he was right, absolutely right. And at that point, I will finish and say thank you for your attention, thank you for your interest.
Jocelyn, for a fascinating recounting of a truly marvellous discovery. I think we've got time for questions, so please, questions.
Dr. Burnell, thanks so much for telling your story. I was wondering, in your career, you've seen how computation has changed astronomy, specifically the analysis of data, a lot of what you talked about. How you were doing as a grad student. I'm wondering, it's very different back when you were a grad student, the kind of processing of data and analysis now using computers. How do you think, like, the computers have helped or potentially hurt the kind of intrinsic kind of connection somebody could potentially have with the data, your notation and your like kind of complete attachment to these charts over the course of this time, like it essentially could catch things that somebody's not constantly looking at the data and relying on that algorithm or something like this.
Yeah, well, computers enable us to analyze a lot more data much faster. Human beings are pretty clever things, but computers can really do bulk data analysis, which means you can get much, much better statistics. But you do need to be alert to what you have asked the computer to do, and in particular what you have not asked the computer to do. It will do what you ask it to do once you get the program right, beautifully, but it won't do any more or any less than that, and it won't do it in a different way. So it's really important that the human brain is also involved in this process so that you can be aware whether you're missing some potential data or something like that.
More questions? Yes, please.
Hi, thank you for the talk. You mentioned that you can tell how many electrons a pulse has passed through. Could you maybe explain how that works? Right,
yes. We see the same effect with light waves when you get spectra and color changes and things. With radio waves, what happens is the radio wave actually gets slightly slowed as it goes past electrons, and how much it's slowed depends on which frequency of radio wave you're talking about. So if you've got several frequencies, you can see the high frequencies are slowed a bit, the middle frequencies quite a lot, and the low frequencies a huge amount. And by seeing how long those different amounts are, you can work out how many electrons there are between you and it. And then you make a guess about how many electrons there are floating around in space and get an estimate of the distance. So it's using a technique called dispersion by electrons.
Could you give us a brief explanation for why the pulsars miss? And so you said you saw it sometimes and you did not.
Indeed. One of the reasons is you're working quite close to the limit of detectability. And you're probably aware that sometimes things can be a bit stronger and sometimes they can be a bit weaker. Some of that change is intrinsic. Some of it is in the propagation as the radio wave comes through to Earth from the thing. But that's basically what's happening. We were working very close to the limits of detectability, and sometimes it poked up above, and sometimes it didn't.
Hans.
Fascinating talk. So were you basically scanning a slit on the sky by, or were you forming a...
Right. The radio telescope shape determines the shape of the beam. And in our case, we had what's sometimes called a fan beam. It's narrow in the direction the stars move. It tends to be wider in the up and down, north and south direction. Yeah. And the exact parameters are determined by the wavelength and by the shape and size of the antenna. But yes, we had a sort of beam like an opened fan.
How long did it take for the astronomical community to come around to the idea that it was a neutron star and not a white dwarf? Did it take until proper measurements of the slowing down were done, or did they come around with earlier than that?
Yes. The proof came when we were able to measure the slowdown rate of one of these pulsars, and that was consistent with it therefore being a rotating object. The debate raged a bit, but I think people were moving towards rotating object even before that proof came.
For the very first pulsar that you observed, is there an optical visibility as well? And if so, you would need a very large telescope for a person with good visual perception to pick it up.
Yes, I'm sorry, I didn't follow up properly on one of my earlier slides. Do you remember me talking about the observatory that was having an open night, and the young woman that looked through and said, "That star's flashing"? That's what we now know as a pulsar in the middle of the Crab Nebula for astronomers. It flashes really rather fast at about 30 hertz. And that's why I was going on about Canada and its 30 hertz. Some young women can see 30 hertz. So there were some people who could physically see the Crab Nebula pulsar flashing. But it's unusual to have light emission as well. They are mostly radio objects, these things. And so your data usually comes out straight into a computer or onto paper chart or something like that.
And the very first one you saw was probably radio only, not visible.
Correct. All my ones were radio only, yeah.
Did your supervisor call anybody else a stupid idiot?
I don't think so, no. He was a bit suspicious about women students. And if I did anything clottish, and you know, grad students do occasionally do some clottish things, yeah, it was "you stupid." Yeah.
How long did it take the press to finally let go of Little Green Men moniker and pick up pulsars?
Oh, I think the Little Green moniker you can still occasionally find. You know, if there is an article about is there life in outer space, this story gets goes in the preface. So I don't think it's ever going to go away, or maybe not ever, but, you know.
Yes. Sorry, this is kind of a more, like, really basic question, but I somewhat understand the reason why there are two beams and why it's focused in one spot, but I was hoping you could, like, elaborate.
She's asking if I can explain why pulsars have narrow beams. This is a topic that has still defeated most people. There are a few theoreticians around who think they understand it, and I think there's a few non-theoreticians who maybe understand their papers, but it's really, really difficult. You are dealing with a highly relativistic system, very strong electric fields, very strong magnetic fields, high speeds of rotation, and it's a stinking physics problem.
First of all, I just wanted to say that your talk is incredibly inspiring and I really enjoyed listening to it. Given the relationship that you have with your advisor, I'm curious how you felt when the Nobel Prize was awarded to him.
Right. Yes. Yes. Interesting. A few years later, the Nobel Prize for Physics went jointly to Martin Ryle, who was the head of the radio astronomy group in Cambridge, and my PhD supervisor. And I can remember that day very, very well. I had just started work in X-ray astronomy. Our X-ray astronomy satellite had launched at 8 o'clock that morning. There was suddenly great activity, you know, the programmers saying, oh, we better get that program working now, it's launched, you know, and things like that. And I was the person who's going to be monitoring and checking the data as it came in. So I'm on high alert, but no data has come in yet. And at about 1 minute past 12, a colleague comes rushing into my office. Have you heard the news? Have you heard the news? Oh my God, the satellite's gone in the drink. It wasn't. It was the announcement of the Nobel Prize. The Physics Prize was awarded to Martin Ryle, who is the head of the Cambridge Radio Astronomy Observatory, and Tony Hewish, my supervisor, for the discovery of pulsars. It was the first time the Physics Committee, Physics Nobel Prize Committee, had ever awarded a physics prize to any astronomers. No astronomers to that point had been considered suitably good at physics to get the physics prize. So this was a real innovation, and I knew instantly that other astronomers would follow and get the Nobel Physics Prize. So I was actually very, very pleased about that. I thought, this is great for astronomy, and I was a little bit proud that it was my stars that finally convinced that committee that there's good physics in astronomy. So I was actually pleased, but sometimes people don't believe me, but I was actually pleased.
Okay, have a couple more questions, I think. Where did you go? Yes.
When doing research, we're taught to, again, thank you very much for the talk. When doing research, we're taught very much to be very mechanical about our analysis.
Yes.
Although when you see the signal, you get excited about little green men, something like that, right? Yeah. I'm wondering about you personally, how much weight you put into, or how much hope you had in thinking that we had found intelligent life versus it just being some sort of mechanical natural phenomenon.
I was really hoping it was not intelligent life, because can you imagine the press hoo-ha if it was intelligent life and there's a young woman involved? You know, I had enough of, you know, please undo your buttons for the photographer. If it had been little green men, it would have been 10 times worse. So.
Question there?
What made you decide to study physics in your undergrad if you knew that you wanted to be?
Sorry, I'm not quite hearing you.
What made you decide to study physics in undergrad if you knew that you wanted to be an astronomer?
Right. Going through high school, it became clear I was good at physics and I liked it. So I was heading for a physics first degree, a bachelor's degree in physics, which I duly did. But along with all that, I'm thinking, what am I going to do with a physics degree? And it was by accident that I came across astronomy through reading one of my father's library books, also by Fred Hoyle, that gent that caused a certain amount of stirring. He wrote some very good books. I read Fred Hoyle's book and was hugely excited. In particular, in physics classes in school, at that particular point, we were doing about motion in a circle, centrifugal force, centripetal force. And here I'm reading in Fred's book about these great galaxies of stars, 100,000 million stars that rotate and have centrifugal force and centripetal force. I can be an astronomer. That's why I'm doing physics. I modified it to be a radio astronomer because optical astronomers work at night and I like my bed. But radio astronomers can work day or night as they choose, as they need to. So I had decided before I left school I was going to be a radio astronomer.
Okay. Last question.
I really enjoyed how you highlighted this trend of like prior to the big breakthrough with pulsars, there were all of these near misses. And in retrospect, we can say that all of these instances in which we inadvertently kind of observed pulsars already.
Yes.
To what extent do you think this is like a generalizable kind of rule that occurs in the scientific process? And do you think it's possible that for a lot of the breakthroughs to come in the future that as of yet have been undiscovered, that maybe we've already inadvertently discovered science?
Yeah, that's a very interesting question. We do occasionally, over coffee wonder if there could be such and such a system that does this, that, or the other, and how would you know, how could you see it? So there is always a bit of conversation like that going on. And it's probably also true that many, maybe only speak for physicists, many physicists, maybe professional physicists, have stored at the back of their mind, there was that experiment that never quite went right. And I never knew why it didn't go right. And it might have been that they were tripping over a new phenomenon that hadn't yet been properly identified. So, yes, thoughtful question. Thank you very much indeed.
Well, please, I would ask you to join me in thanking Professor Bell Burnell for a wonderful and inspiring talk, and also for the wisdom in the answers to your splendid questions. So thank you very much.
Thank you. Thank you very much. Thank you. Thank you very much.
Thank you so much. I don't know what to do.